Assalamualaikum and salam sejahtera to everyone. My name is NURUL FITRI binti Iriani. The purpose of this video is because I will be presenting my research project titled Determination of Manning'S Roughness Coefficient by Cowan method for floodplain at Kota. This research was conducted under the supervision of Dr. Nazirah Muhammad Tarmizi, who has guided me throughout the methodology, analysis and development of this study. On my left is the official research poster that I prepare and submit for the grid competition. However, since the details on the poster may not be clearly visible through this format, I will explain each section of the study through individual slides for better understanding. Nonetheless, the poster is included as part of my official submission. This study focused on identifying and calculating Manning'S roughness coefficient using the Cowan method supported by land use land cover LULC data from satellite imagery for the floodplain area in Kota Kedah. Now, moving on to the abstract of the study. This section provides a brief summary of the entire research. This abstract says that Manning'S roughness coefficient is resistant of flow channels and floodplains. Roughness is usually displayed in the form of Manning'S and value. The material and state of the channel or channel affect Manning'S and values, which are determined by empirical observations. Common materials with different roughness qualities include asphalt, concrete, and different kinds of vegetation. For example, thick vegetation can produce values as high as 0.050 to 0.120 depending on the density and height of the plants involved, whereas average end values for concrete pipes vary from 0.011 to 0.015. The aim of this study is to identify the Manning'S and value for mixed development area using remotely sensed data. The first objective of this study is to identify the parameter related to Manning'S roughness coefficient. Secondly, to using remotely sensed data in Alustar, Kedah, Malaysia by Cowan method. Technology for remote sensing provides an effective instrument to observe and analyze the material and roughness and values across numerous in order extents and huge real distance. The data obtained through use of remote sensing will then be used to obtain the value of Manning'S N. The expected outcome of the study is to reveal the variation in Manning'S roughness coefficient. It can show that Manning'S N varies greatly depending on the area and occurrence within the mixed development area in Alustar. In addition, through this study, we can also analyze how different shapes of channels and structures will affect the roughness coefficient. The result of the study will have significant implication for the parties involved as National Disaster Management Agency (NAMA), the Department of Irrigation and Drainage (TPS), and Town and Country Planning Department Plan Malaysia, along with achieving SDG 11. Now, let's proceed to the introduction and objective of the study. First is the introduction, where every river is unique and constantly changing, and these changes affect the environment and can lead to flooding. Specifically, the type and roughness of surface materials influence how water moves, which is rougher surface slow down water flow and increase flood risk. Therefore, Manning'S roughness coefficient or N value helps measure how different surface, vegetation and river characteristics affect water movement. One common way to estimate Manning'S N is Cowan method, which calculates the coefficient by combining factors such as surface materials, vegetation, flow obstructions and surface irregularity. This approach provided a more accurate value by considering multiple elements that influence flow resistance. In addition, mixed-use development that combine residential, commercial and industrial areas are common in Malaysia and can significantly change river flow patterns. As a result, large-scale development increases land use, which may cause more frequent flooding and environmental changes. Next, I will highlight the objective of the research, which are the first one is to classify typical values for Manning'S N for different waterways using remotely sensed land use land cover LULC based on the parameters that contribute to Manning'S roughness coefficient of the study. While the next one is to determine the N value of Manning'S at a mixed development area in Kota, Malaysia by Cowan method. Moving on to the next part of the presentation, the problem statement and the novelty of the study. This section explains the key challenge that motivate the research and highlights what makes this study unique compared to previous works. For the problem statement, in any flood modeling study, one of the key components that influence the accuracy of prediction is the Manning'S roughness coefficient. This value represents the resistance that water experiences as it flows over various surfaces, and it directly affects how fast or slow the water moves and how much flood risk a given area faces. To simulate flood events accurately, Manning'S and value must be defined appropriately depending on the type of land surface. If the value is not accurate, then the prediction of water levels and flow paths during a flood can be significantly off, leading to misinformed flood risk assessment. However, the main challenge is that Manning'S n is not a fixed value. It varies greatly across different types of surfaces and environment conditions. For instance, a forested area will have a higher roughness compared to bare land. To support this study, I refer to several key sources that focus on estimating Manning'S roughness coefficient and the tools commonly used for this purpose. First, the Cowan method introduced by Cowan in 1956 is a well-established approach that estimates Manning'S n by breaking it down into several contributing factors such as the basic surface roughness, vegetation cover, channel irregularities, obstruction, and channel alignment. Unlike other methods, Cowan's approach does not rely on hydraulic parameters like flow, speed, or channel size. This makes it especially useful when we only have access to land surface data. Next, the study by Hossein, Jia, and Chow in 2009 highlights how Landsat-8 satellite imagery can be effectively used to generate accurate land use land cover maps. These maps are essential in flood risk studies because different surface types influence how quickly water can flow. Lastly, Arsman and Schneider 1984 emphasized the importance of accurately estimating Manning'S n for reliable hydraulic and flood modeling. They proposed that combining field-based methods like Cowan's with GIS and remote sensing data provides a more precise estimate of surface roughness, especially in complex and dynamic environments such as floodplains. Now, let's go through to the materials and methodologies used in this study to obtain the Manning'S and values for the Kota Star floodplain. The study area that I choose is Kota Star in Kedah, as shown in the location map. This area was selected due to its diverse land use type and flood-prone characteristic. Next, let me explain the workflow for the study as shown in the flowchart on the right side of the slide. The process begins with the planning phase where the overall research design, study objective, and data requirements are outlined. After that, I move into the data acquisition and pre-processing stage. This involved by collecting Landsat-8 satellite imagery for the study area. Before any analysis could be done, the raw satellite data had to be prepared through several pre-processing steps, which are layer stacking, subset, geometric correction, radiometric correction, which included haze reduction to eliminate atmospheric interference and enhance image clarity. Next, in the data processing phase, I conducted supervised classification to produce the land use land cover map. This classification involved training the system to recognize different land types such as commercial area, settlement area, cultivated area, grassland, and sparse forest, based on the reflectance values. Once the LUSC map complete, I identified and assigned appropriate Manning'S and value to each land cover class using the Cowan method. This step considers several roughness factors including base surface, vegetation, and obstruction. The process then continued to the result and analysis phase, where I calculate the total area for each land cover type and use the weighted average Manning'S n formula to derive the average roughness coefficient for the whole study area. Next, I apply the Cowan method formula to calculate the Manning'S n value, which represents surface roughness. Proceed to the table in the study. N2 was set to 0 because of the shape and size of the river channel were not considered as the focus is on the floodplain surface. Meanwhile, M was set to 1.0 since the selected area consists of relatively straight river with only slight meandering. Once the individual N values were calculated for all land cover types, I used a weighted average formula to get the overall roughness value for the study area. These final average values give a more realistic estimate of surface resistance, which is critical for hydrological modeling and predicting flood behavior. Now, let's take a look at the result of the study. This map shows the distribution of Manning'S roughness coefficient value across the floodplain of Kota. This map was generated based on land use land cover classifications, where each class is assigned its respective Manning'S value using the Cowan method. The different colors represent different land cover types. From the map, it's evident that commercial areas and settlement areas dominate, showing that urban and built-up surface make up the majority of the floodplain. These surfaces typically have low surface roughness, which contribute to higher water flow during heavy rainfall or flooding events. In contrast, green and dark green areas, which represent vegetated surface with higher roughness, are noticeably limited in coverage. These areas play a crucial value in slowing down water flow, helping to absorb runoff and reduce flow intensity. By visualizing the distribution in this way, we can clearly identify which areas are more vulnerable to rapid water flow and where flood prevention may be required, particularly in areas that are heavily urbanized. On the right, we can see a bar chart that illustrates the percentage of area for each land cover class. Based on the table, urban areas such as settlement and commercial areas dominate the floodplain and have lower N values. This smoother surface cause water to flow more rapidly towards the sea. Therefore, if the drainage system is adequate, the fast flow can potentially shorten the flood water recession time. However, the rapid surface runoff in urbanized area also increases the risk of flash floods, especially if stormwater drainage is insufficient. Below that, the table shows the calculated average Manning'S N for the entire study area using the weighted formula, where the result is 0.0568. This value reflects the overall surface roughness in the floodplain, which is relatively low, again highlighting a potential flood risk in the area. Overall, the findings confirm that urbanization and land use pattern greatly influence surface roughness. Vegetated areas like grassland and forest play crucial roles in slowing down water flow and reducing flood risk. Now, let's jump to the discussion. Start with the importance of Manning'S N. Study highlights how importance of Manning'S roughness coefficient N in modeling and preventing risk of floods. An accurate estimate of N is required for estimating water flow and floodplain behavior, which has direct impact on flood prevention techniques. However, to improve the reliability of the study this method, future research should consider doing field validation using higher resolution image or comparing Cowan's method with other estimation techniques to check for consistency. The last one is a conclusion. To sum up what I have achieved, the study successfully achieved its objective by classifying Manning'S roughness coefficient values using remote sensing LULC data and determining Manning'S N in Kota mixed development area with the Cowan method. This information is crucial because it gives benefit to the public by offering clearer flood risk and water flow information, enabling authorities and communities to make right decisions to protect property and lives. That concludes my presentation for this script poster. To end, I have included the complete poster that I have developed. Thank you for your kind attention and consideration, and I truly appreciate the time and effort of the panel and judges. Thank you.